Well, good morning, good afternoon, good evening, wherever you are in the world. Welcome once again to Photonics for Quantum 2. And this is a special day. This is the very last talk, and we saved the best for last. So we've had an exciting time. We've had a great time hosting these talks. We've learned a lot. They're all recorded, and you can get them online at our webpage. You can just Google RIT Photonics for Quantum 2. That'll lead you to the webpage, and then click on whichever talk you want to see. You'll see a little drop down and then a link for the videos. You also can download the slides. There's another link for the slides. So for the last time, let me thank from the bottom of my heart all of our sponsors who generously contributed funding so that we could provide this content to you for free. And surrounding me, you can see their beautiful, colorful logos. So thank you, everyone. Thank you to the sponsors for supporting us in this workshop. Also, if you go to the Photonics for Quantum 2 webpage, there's a link for the sponsor exhibition hall. It's a virtual exhibition hall, and you can click on that and view some materials from our sponsors, including their web pages and some videos. So, introducing today's speaker, the final speaker, Cindy Regal from University of Colorado Boulder. She's going to tell us about the newly awarded NSF Quantum Leap Challenge Institute that was awarded to Colorado Boulder, and we're very excited to have her. So Cindy, thank you. I can see you there. So go ahead and share your slides and I'll let you know if we can see them.
All right, great, thank you. Let me work on the sharing here. Okay.
Yes, I can see the slide. Take it away, thanks.
Okay, great. Let me just go to presentation mode here. There we go. Okay, great. Alrighty, we should even have a laser pointer going now as well. So,
yep, I can see that.
Thank you very much for the invitation and the introduction. It sounds like a exciting series. And what I'll tell you about today is, as Don said, our newly awarded NSF Quantum Leap Challenge Institute focused on quantum sensing. Our acronym is QSense, Quantum Systems Through Entangled Science and Engineering. The entangled science and engineering being shorthand for we're really trying to bring science and engineering together in a way that physicists and quantum systems have not in the past. And so, we're certainly very excited and grateful to NSF for being able to embark on this science within a very national team. As you can see from this map here, this is all the institutions that are involved in our institute. And so today I'll try to tell you a story that ranges from our scientific vision to logistically how we hope to bring many elements together in this rather large center. Okay, let's start with a little bit of context here. If the slides will advance, there we go. In terms of backdrop for this talk, why am I here today? So the PI of this proposal is Jun Ye. And so he leads this rather large center involving 37 investigators at these institutions I just showed. Jun is an expert in all things quantum sensing, specializes in optical atomic clocks, ultra-cold molecules, quantum metrology. And he's also the director of our local initiative called Qubit, spelled C-U-BIT, that I'll tell you about in a moment. And so my role in all of this, so maybe just in a little bit of introduction to myself. So this is a very sprawling, large endeavor. And I'm the Associate Director for Science at our local initiative, Qubit, CUBIT. And I've sort of in this way taken on the role as helping lead research convergence for this QLCI Center. So that's why I'm here talking to you today, because there's sort of a large team of people who put this together. And we share all the opportunities to come tell people about it. My specific research is in neutral atom quantum bits in optical tweezers, as well as micromechanical quantum systems. So a variety of quantum and quantum optics type problems. So I'm an experimentalist. Okay, and I'm an associate professor in the physics department and also a fellow of GILA, which is one of the institutes on the University of Colorado campus. So one context that's sort of helpful that is not specifically this QLCI, but a little bit the backdrop of how we organize things at Colorado is we have this CU-BIT initiative. And the goal of this is to partner with regional universities and laboratories that contribute complementary strengths within quantum, link closely with quantum intensive companies nationally and especially locally, and then serve a spectrum of local, regional, and national interests, including workforce development and education. So this initiative here is not itself QLCI, which is a national center, but it's helped form some of the framework that has helped us put some of this together. Okay. That's why the advancing doesn't work sometimes. There we go. Okay. So like I said, though, what I'd like to tell you about today is this NSF QLCI for quantum sensing. And Don said to mention as well, if people want to ask questions as we go along about scientific or programmatic things, feel free. I'm not entirely certain if things pop up in the chat box that I immediately see it. So however you'd like to flag me, go ahead. Okay. All right, so in all of these Quantum Leap Challenge Institutes, the goal is to head towards an impactful quantum revolution, a quantum 2.0. I noticed that's the title of your conference. And many of these things can be described as sort of a quantum speed up for breakthrough discoveries in science. And that can take many different roles from quantum computing and networking and simulation and many-body physics and understanding chemistry problems, and in our case, sensing problems. And our approach to trying to head towards a breakthrough discovery is we focus on what we think as some of the leading qubit technologies, atoms and ions that we've had a lot of focus on in Boulder, Colorado over the years, but also superconducting devices. And of course, these span a range of a two-dimensional parameter space of qubit coherence and qubit control. And the goal is really to bring these systems from demonstrations of certain quantum properties at the few particle level to really quantum systems of many particles. And that's a monumental task, right, that faces all of us in the quantum community. But how you create these quantum systems and what they can do, we think especially in quantum sensing, there's ways to create these systems, utilize entanglement and squeezing, and move towards the realm of discovery. So, in this sense, especially for Boulder that has a lot of historical connection to metrology, quantum sensing sort of hits a sweet spot for us. In terms of being able to look at challenging problems like searching for dark matter, but then also connecting to simulation, computing, networking, and defining sort of the next frontier for measurements and discovering new physics. We think that the type of technology that we're developing is not just for fundamental physics, but new technologies that will have immediate impact. And we think quantum sensing is also a nice platform in which to train a quantum workforce, which is part of what the goal is in this quantum initiative. Okay. So the way that we've set up our center is through 3 interconnected challenges. And the bottom one on the left here, I'll try to use my pointer a little bit more, is sort of the meat of the science using quantum advantage in sensing and measurement. And then we get into deployable sensing and measurement that has an even more connection to engineering. And then we would think we have a rather unique aspect over here, which is helping to form a national quantum infrastructure specific to forming some standards regarding metrology and quantum sensing in certain atomic platforms. So what I'll do is I'll try to go through each of these 3 areas, but I'll also give you a little overview of how they're sort of all connected. And my button doesn't work very well, but okay, there we go. So first of all, in terms of scientific and geographic connections in our center, So as I've said before, we really try to put a pretty large emphasis on the connection between quantum science and engineering. So we really want to have that overlap. And I do not know why this is sometimes just not advancing. There we go. Okay, we want to overlap with a variety of scientific themes. For example, searching for dark matter. We want to overlap with a variety of different types of sensors, from atomic sensors to superconducting circuits, and other platforms as well. As I mentioned at the beginning, it's a national center with quite a few both institutes, national laboratories, and universities. So we have NIST and the University of Colorado in the Boulder, Colorado area. We have a number of Western national labs and universities. And we have also a number of East Coast universities and Lincoln Lab as well, and some overseas collaborators in addition. So this is all based upon, trying to form a central theme related to quantum sensing goals, where we can search for new physics and also bring engineering into the picture. Okay. Alrighty, not advancing again. I don't know why this, there we go. Okay, there it is. Okay, so the next slide here is, another important aspect of how we set up our integral aspects is how do we have an impact on the quantum economy? And we've taken as a model some of the impact that we've had in the past, which is really through students making an impact on startup and other companies. These are a few examples of some startups related to atoms and optical tweezers, to photonic things, to sensing such as AOSense. And then larger corporations like Honeywell have set up quantum focused aspects in the Boulder area. So this has been very interesting as well. And we feel like QSense, we want to continue to push this forward of bringing students to the workforce in a variety of endeavors. And so I'll save a fair amount of time at the end of this presentation for a detailed plan of our educational paths for the center. Okay. But I wanted to start off the sort of more detailed discussion of our interests by talking about the meat of the science, which is quantum advantage in sensing and measurement, and giving you a flavor of what does that really mean. So our guiding principle is to deliver near-term science and technology benefits from sensors that are harnessing entanglement. And these entangled sensors include atoms, ions, circuits, and molecules. And to give you one example of one way in which squeezing an entanglement can help improve certain precision measurement searches, I'm going to give you one example that's related to quantum electrical circuits used to accelerate a search for dark matter. And these are some slides that were put together by Conrad Leonard, who leads the thrust of entangled sensors within the center. And advance. I wonder if I can find a different button that does this. Maybe it's this pointer's problem. Let me see. Okay. All right. I think I'm going to dispense with the laser pointer because maybe that's what's causing the problem. Okay. So one of the big questions that's out there is what is the nature of dark matter? And I'm not an expert in this, but certainly it's very clear that dark matter is a great mystery. It's 85% of the matter in the universe. It's detected only gravitationally. And there's many, many different possibilities for where dark matter could come from. And one sort of portion of the search for dark matter is in the realm of ultralight dark matter. And in the example that I'll talk about, this is axion type fields. So in the context of ultralight dark matter, you have sort of a more field-like than particle-like system. And so the tone of a search for ultralight dark matter is you're looking for something that's feeble, it's persistent, and it's really at an unknown frequency. And many of these searches for ultralight dark matter can benefit from entangled sensors. And so, oops, there we go. So we have a number of different such searches within the context of our center, involving molecular systems, atomic spin ensembles, and microwave cavities is the case I'll talk about briefly here. So in this particular sort of type of dark matter detection, you're looking for basically a classical force acting on a quantum harmonic oscillator, which is this microwave cavity. And so the dark matter should have an impact on this high Q tunable oscillator in the gigahertz regime. So you should have some signal sort of appear in this microwave cavity that's very feeble. And there's many different searches that are taking this approach. And in all of these, if I look at this in quadrature space, then I imagine my dark matter signal looks like a displacement as shown. And quantum noise certainly plays a role in how well I can detect this very feeble signal. So in the context of a search where you have no idea what frequency this signal is, if I have to scan in the, say, 1 to 10 gigahertz range at the quantum limit, this is ends up being lots of time and lots of money. And it turns out there are ways to actually squeeze microwave signals with things like Josephson parametric amplifiers. And in this way, searches of this type have been speeded up by, say, a factor of 2 from squeezing in these microwave systems. So that's sort of an example of something in the past. And in the future, if I can get it to show up. Okay, the future holds a lot more that can be established in the context of entanglement and squeezing using distributed entanglement, microwave photon counting. So there's a lot to explore to really accelerate these very difficult searches. And we have sort of very similar stories in the context of many different platforms within our center. So let me list some of the other sort of platforms that all have rather similar stories, ranging from optical lattice clocks that June is an expert in, ion clocks in computing, atom interferometers, nanowire single photon detectors, magnetometers, and molecules. So these are all experimental platforms that are represented in the center. And I don't talk about it a lot so far, but we also clearly have a cross-cutting theory, both within quantum information science, but also machine learning and atomic spectroscopy and precision measurement. And in all of these stories, I sort of think of there being two sides of the coin. On one side of the coin, we can develop these sensors for fundamental physics, searching for gravitational waves in certain bands, these dark matter searches, looking at many-body quantum physics. But then the other side of the coin is that there are really practical applications for these things as well, from inertial sensors to brain imaging, to ways to read out qubits better, which ultimately impact things like quantum computing. And in this coin analogy, I was trying to decide if the head or the tail should be the more practical or more fundamental, and I wasn't exactly certain, but that's what I decided on. All right, let's see. So yeah, that sort of brings us a little bit to how we sort of bring together science and engineering together in the center. And this brings us to our other thrusts like deployable sensing and measurement and the national quantum infrastructure. Okay, let me check my chat just once, just to check there's no questions. Looks like not. Okay. All right, so in terms of deployable distributed sensing, this is one of our grand challenges. So the guiding principle here is for quantum sensing technology to truly have an impact, it must reach the field and ultimately the hands of end users. That's not always the case for current technologies. You know, how do you take a typical laboratory scale experiment and turn it into something that's more in the realm of users and engineers? So the way that we focus on this is through extensive collaboration between scientists and engineers, a mix of quantum and enabling classical technology advances, and involving the expert sort of end users, for example, in navigation and timing. We have some people from University of Colorado who are in the aerospace department who can help to guide some of this development. Okay. So one example of, one way in which the
Well, looks like Cindy froze up from my perspective. Is that true for all of you? Oh, hi, Cindy. You're back.
hello.
It looked like you froze up for just a second there,
Oh, okay.
but you're back. But by the way, when you hover your mouse in the lower left of your slide, I
Yeah.
see some controls pop up, and it looks like there are some arrows. Do those things advance the slides,
Yeah.
or are they not easily usable?
Let me try that. Yeah. Okay.
Well, I
That.
don't know if that helps you. But by the way, when you had to decide what was on the front or the back of the coin, you should have flipped a coin.
That's true. That's true. Yes. Okay. All right. Well, let me back up one slide here since my controls are now working. I never had problems with the other arrows before, but yes, now that my Zoom is not covering them, I will use the PowerPoint arrows here. Okay. All right. So I didn't freeze up before this slide, did I?
No, you were talking about that slide.
Okay. Great. Perfect. All right. So in terms of the two sides of a coin type analogy, in our center we have people who are pursuing the most precise and accurate clocks out there that can look for new signatures in fundamental physics. But we also have, based upon the same clock technology, really trying to push these sensors to be portable. An example of this is making compact clocks based upon optical transitions in alkaline earth atoms, such as ytterbium and strontium. And so this is a picture of one of the sort of integrated photonic couplers that we hope to use to create light for atom trapping. And we also have groups that focus on integrated frequency combs and light sources that will be used to make a small package portable sensor that will ultimately part of a larger goal to impact sort of PNT research. Okay. All right, I'll use the right advancer here. All right, and then sort of another aspect of our focus in terms of how we hope to really advance engineering in the context of the center is our focus on national quantum infrastructure. And what does infrastructure really mean here? It's a little bit different than sort of any aspect of a proposal that I've been on before. And the guiding principle here is to build a long-term national quantum infrastructure for computing, simulation, and sensing, picking the atom strontium. And the idea here is to accelerate some standardization of quantum technology for early commercialization. And the idea is not just for example, the portable clock example that I just showed you, but for general components that are of use to many situations, from a range of academic laboratories to sensors used in industry to big projects in national labs. And this idea of standardization is sort of scary in the quantum realm these days because there's so many unknowns about how we really make quantum systems work that it's hard sometimes to pick a platform, but it's very useful, especially when you want to interface with industry. And so picking strontium, it may be the right atom choice and it may not be the right atom choice, but it's good to make a choice to enable this standardization. Okay. So as a couple of examples of why picking an atom and sort of pushing forward an infrastructure could be useful, in terms of quantum computing and simulation, strontium has become quite a popular atom. There's a lot of vibrant research and development as strontium as a qubit, both in academia and also in industry now. And there, instead of specifically looking at the clock properties based upon ultra-narrow atomic transitions, we're harnessing atomic structure and these same atomic transitions in order to make better qubits. And so there's some work with strontium atoms and optical tweezers, where each of these can be individually addressed and serve as qubits and Rydberg excitations and enabling interactions. And then also, even in the context of industry, for example, this company, Atom Computing, is creating arrays of single strontium atoms also to be used as qubits. And so you can imagine that both of these types of endeavors really require some standard technologies. On sort of a very different scale, there's a big science connection to strontium as a precision sensor. So there are large-scale atom interferometers with strontium being built, for example, at Fermilab with the MAGIS 100 detector. And in these experiments as well, our QLCI strontium infrastructure focus should inform sort of a backdrop for transitioning academic research to national labs. Okay, so that sort of segues into our plan for education and workforce. And I told you I'd leave a decent amount of time in this portion of the talk in order to emphasize how important this is to us and how we hope to push forward education on a number of different fronts. Heather Lewandowski is an expert in physics education research who has put together a lot of the ideas for how we not only come up with a set of programs, but we come up with a set of ways that we can sort of determine if those programs are being effective through education research techniques. So here's sort of a bullet list of all of the different aspects that we hope to really put into our education plan that will form this pipeline that will bring people out to the quantum workforce. So we're going to have a professional master's and stackable credits in quantum engineering. So really bringing the engineering department into this in this way. Having industry and national lab internships, interdisciplinary graduate training, a quantum track in our physics PhD program that has courses that are much more tailored to quantum information. Community college partnerships, an undergraduate minor in quantum science and engineering. We have a very large engineering population at the University of Colorado, and we hope to introduce this minor there. This quantum forge idea up here, I'll talk about that a little bit later, but that's one of the unique hands-on experiences that we hope to have in the context of the center. And then we also are partnering with PhET, where they do interactive educational modules that I don't know if you've used in your courses before, but there will be some specific focus on quantum opportunities in that space. Okay, and we hope to really sort of encompass all of this with education, research, and evaluation, so we know the efficacy of these programs. All right, so prior to the proposal stage, we really wanted to understand how do we address the needs of quantum industry. So Heather really focused on how do we get the information that's needed. So there were interviews that were conducted with 21 companies in quantum industry through the QEDC members. And there were a number of things that people really wanted to emphasize in terms of shared skills that people were interested in across the whole quantum industry. So they're interested in workforce with classical coding skills, statistics and data analysis skills, laboratory experience, electronics, troubleshooting, problem solving, and quantum algorithms and computer science. So we got some information about what are different priorities in the quantum industry. And some interesting quotes that came out of these types of interviews. With things like, currently the only place to get a high level training is by getting a PhD in physics. And we're just about bringing enough PhDs in physics to satisfy the workforce needs of the industry. So anything other than that would be a welcome idea because that supply chain is simply insufficient. So understanding which supply chain is insufficient from the perspective of industry was helpful for us. Okay. So from this perspective, this professional master's program will be developed in the context of engineering, and will include courses like fundamentals of quantum mechanics for engineers, quantum device engineering, quantum photonics, and it's meant for sort of a more professional community. It'll include stackable credentials, and in terms of just different courses that are now going to be offered, basic course in quantum information for engineers is something that has not existed, at least at our institution, and that we hopefully can push forward. Okay, and the content that is often most valuable for companies is students gaining hands-on experience. This is another thing that we learned through these interviews. All right, yeah, so then in terms of PhD training, the University of New Mexico has for a very long time been a very strong leader in theory and quantum information science, and they have really taken the lead in thinking about graduate quantum certification for PhD programs across the spectrum. And so they have things like a universal primary course on the fundamentals of quantum information science, and then specialty graduate electives across departments and colleges. And we hope that we can start there and use this as a template for other universities within the collaboration. We also hope to have a student research exchange marketplace that matches students with internship opportunities with partners at national labs and within industry. Okay, and then in terms of undergraduate education, there were quotes, again, from these industry interviews that said things like, I think that there could be sort of a 1 or 2 semester course at the undergraduate level, which could start producing people who are basically primarily experts in some other traditional engineering subject, but who also have a basic grounding in quantum information. So in terms of hearing this comment, we're introducing an interdisciplinary minor in quantum science and engineering that will have courses in introductory quantum engineering, quantum physics, experimental skills, in addition to the sort of primary subfield of the student. We're also developing quantum engineering modules for 2-year colleges. For example, Front Range Community College, which is a local 2-year institution. So this brings us to the idea of this quantum forge, as we call it. And the idea of this is, addressing the type of ideas that folks who can design an experimental program, go and implement it, take the data, understand what the data says, and then decide what the next steps are after that. Yeah, that's a really hard thing to learn and do. And how do you really teach that? And the Quantum Forge is going to involve teams of 4 to 5 science and engineering majors working on a 1 to 2 semester project from academic groups and industrial partners. This is somewhat formulated after some programs we already have in our engineering school. And we think this sort of puts an educational piece in between 2 wildly sort of differing types of experiences. So lab courses on the one hand, right, that are very guided, and undergraduate research on the other hand that's open-ended, but there's only so many students that you can involve in typical undergraduate research experiences. So the Quantum Forge will lie in between, and it'll be open-ended, outcome unknown research, but hopefully a more scalable type system. All right, and then lastly, in the context of building a quantum literate citizenry, we're collaborating with PhET that does free interactive science simulations for K through 12 and college, includes lesson materials and accessibility, research-based design, and so we will be embarking on QLCI related ideas and PhET interactive simulations. Okay, and as you know, just as sort of this circle of science and engineering defined how we do things in the context of our science, in the context of our education, we also focus on research and evaluation that will define goals, measure outcomes, and develop programs. We hope this will go along in a productive circle. And we hope that there'll be broader outcomes that include effective practices for developing and implementing quantum education and workforce training programs. And the consumers of this, I referred to a lot of programs that are very university specific, right? Because it's hard to develop this uniformly across all institutions, but it's very important that it's shared with other centers and universities, QEDC members and educators across the spectrum. All right, well, I think I'm getting close to the end of my time here, so that's pretty good timing. I wanted to sort of end with a couple of things. First, an acknowledgement that I've gone through a lot of different material here and big visions on a number of contexts, and what is really behind this is a very cohesive and tireless team of principal investigators and investigators within the center, and you can see all of their names here. They come from many different institutions, as I said, both universities and as well as national labs and institutes. And these lines are meant to represent all of our cross collaborations that really sort of make us a cohesive team. And of course, this comes together with many educational and industry partners. So in the end, the summary of our QSense, Quantum Leap Challenge Institute, is we're looking for a broad quantum workforce, as well as to study diverse sensors with quantum advantage that can look at fundamental physics. We hope to end up with addressable and programmable quantum systems impacting not just sensing, which is important to have as a focus, but also we'll have inroads in networking, computing, and simulation using both atoms, ions, as well as superconducting circuits. So with that, I think that's the end of the main presentation here, but I'm happy to answer any questions.
Okay, Cindy, I'm clapping on behalf of everyone who's muted. And it looks like, thanks for a fantastic presentation. That was an excellent overview of everything you guys are doing. Can you see the chat box? Because there's a question there. Someone is eager to join and help.
Open the chat box here now. Great. Okay, let's see. The flip coin, that's not a question, that's a comment. Okay, all right, so an education program question. I don't know, is it possible to so Alex is asking about the education program and you know, how can one help with the teaching in the context of this education program? Yeah, that's a good question. Shall we, Alex, do you want to be able to chat one-on-one, or should I try to answer that on the chat, or basically back to the chat?
Well, you could just say in words what your answer would be. We also let people join and show their video if they'd like, but it's not necessary.
Yeah, no, I mean, in terms of how overarching we think about the teaching and the programmatics and the undergraduate curriculum and the graduate curriculum. And, you know, I would say one of the biggest pieces that we found in terms of, you know, what is the most challenging course that we do not have that we need to design? And it's really these undergraduate and master's levels courses that are either, you know, it's a computer scientist and they, you know, they've never taken modern physics, but they've taken linear algebra. How do you design a course that teaches quantum mechanics to that set of people? Similarly with electrical engineering, right? You know the basics of that field, but again, maybe haven't taken modern physics. How do you explain quantum systems to that community? So I would say that in terms of teaching and course development, that's our biggest challenge. And so I think any ways that we can connect to people who are making inroads there would be great.
Thank you.
Okay, all right, next question was another one on education. Give an example of a quantum forge problem, and are you going to ask students to identify interesting problems, or faculty does that? So we hope to sort of start from something that we know well in Boulder and sort of work towards something that we're less familiar with and the thing that we know well actually is in the context of a lot of these precision metrology problems, there's a lot of very specific electronic problems that are both digital and analog. And for a very long time in Boulder, we've also had very specific engineering support staff who help work on those problems. So we help to sort of form a set of problems that are in between faculty definitions and these engineer definitions to help really sort of push forward the sort of, for example, the control circuitry related to optical atomic clocks. So I think that's one example we're very familiar with and we think we can make scalable projects based upon, and we have the sort of knowledge to do that in a somewhat scalable way. But on the other hand, what we're hoping to do as a function of time is really turn this a little bit more into what our engineering school does right now, which is they actually partner with industry, small companies will sort of sponsor these quantum forge problems, and the companies may actually define some of these problems in that case. And how the students will find the right resources, how they'll interact with the company, but also with faculty. That's part of the challenge of the Quantum Forge, but something that we hope to overcome. All right, let's see. Okay, another question on education. So let's see, speaking of the pipeline, we have geographical race segregation across the country. Is there a plan to ensure typically underrepresented communities are included? That's a very good question. And you know, we do have some geographic diversity, but not, there's certainly a big gap in that. And so I think the University of New Mexico has been very proactive in this area, and we hope to learn from some of the things that they're doing. In particular, their interdisciplinary quantum programs. They've really tried to bring in underrepresented groups to physics sort of through other disciplines. And I think that is a nice thing, though I'm not an expert on their program. So it would be good if Ivan Deutscher or someone from there was here to answer this question. But I think that is something that we definitely have to think about. And there's many ways in which our community college partnerships, but probably more partnerships are required for us to really do this right. Okay, all right, next question. The quantum industry puts classical coding and statistics ahead of quantum experimental skills, but the education program addresses the importance of quantum. How do you solve this mismatch? Yes, that is a hard mismatch. And I think the main way that I would say that it's sort of coming at it from the flip side, which is if we go back to, I think our undergraduate minor thing, it's a good example. What is that? There we go. Okay, so the idea of this, the undergraduate minor in quantum, is sort of to turn that problem on its head. It's sort of saying, if quantum industry mostly wants people who know how to code and know experimental skills and know statistics, you know, these people don't have to come from physics. They can come from electrical engineering, or they can come from computer science, or that may be really where their degree should come from. But they can't go to a quantum company, or at least I think the feedback we got is they can't go to a quantum company with zero knowledge of quantum, right? They won't have a context for those type of companies or context for what is trying to be done. So this sort of flips it on its head in terms of mostly you learn some other thing, but you know enough about quantum to sort of be able to operate in that space. At least that's the idea. Okay.
Okay, Cindy, it looks like that's it. And just wait a few seconds for any last takers. Okay, it looks like that's it. Thank you so much for giving an excellent talk and giving us an insight into your new center. Congratulations to you and everyone on your team. And for all the participants here, thank you for joining us. It's been a pleasure hosting these, and we'll see you again next year at PFQ3, hopefully in person, probably next summer where it's warm here in Rochester. So long, Cindy, and so long to all the participants. Goodbye.
Thank you very much.